Welcome to a modern-day fairy tale in computer architecture, where the story of the Tensor Processing Unit, or TPU, unfolds. This is a journey that weaves together decades of innovation, the relentless pursuit of performance, and the vision of some of the brightest minds in technology. From humble beginnings in university labs to the heart of Google's data centers, the TPU has become a symbol of compute intensity and efficiency. Today, we'll explore how a PhD thesis from 1978, a groundbreaking patent, and a series of pivotal collaborations led to a 100x leap in peak TPU TFLOPs over just 10 years. Let's dive into the origins, rise, and evolution of the TPU. Our story begins in the early 1980s with a pivotal invention, the systolic array for matrix computations. In 1983, a patent was filed by Kung and colleagues, laying the groundwork for what would become a revolution in parallel processing. This technology enabled efficient matrix operations, a core requirement for neural networks and deep learning. The systolic array concept would later become the heart of the TPU, allowing for massive parallelism and high throughput. This early innovation set the stage for decades of progress, influencing both academic research and industry applications. The TPU's roots are intertwined with the careers of three remarkable individuals: H.T. Kung, Charles Leiserson, and David Patterson. Kung, a mathematics student from Taiwan, specialized in analytical solutions for complex numerical systems. Leiserson, a Ford scholar from Norway, became a domain authority on algorithms and computer architecture. Patterson, a wrestler and math student, would go on to co-invent RISC and RAID, shaping the future of microprocessors. Their paths crossed at Carnegie Mellon University in the 1972, and their collaborative work would eventually lead to the creation of the TPU. Their influence extended far beyond academia, shaping the very fabric of modern computing. As these pioneers moved from university labs to industry, their research began to influence real-world systems. Kung and Leiserson's work on parallel and distributed computing, along with Patterson's contributions to microprocessor design, laid the foundation for the next generation of computing hardware. Their collaborations, including joint papers and patents, would eventually inspire the architecture behind Google's Tensor Processing Unit. The TPU story is not just about technology, but about the intersections of ideas, disciplines, and people, all converging to solve the challenges of computation at scale. Fast forward to 2013, Google's data centers were facing a new challenge: the explosive growth of deep neural network workloads. While CPUs and GPUs had served well, the demands of training and inference for AI models were quickly outpacing existing hardware. Google realized that if just a small percentage of users increased their use of voice search, the compute load would double, making DNN usage unsustainable. This triggered the search for a new kind of processor, one that could deliver unprecedented compute intensity and efficiency for neural network tasks. To address these challenges, Google turned to application-specific integrated circuits, ASICs, and domain-specific architectures, DSAs. Unlike general-purpose CPUs or even GPUs, ASICs are tailored for specific tasks, offering much higher throughput and efficiency. For Google, the specialized task was deep neural network inference and training. By focusing on the unique requirements of matrix multiplication and addition, the TPU was designed to maximize performance for AI workloads, setting it apart from traditional processors. Neural network workloads fall into two main categories: training and inference. Training involves adjusting model weights to recognize patterns in data, a process that is computationally intensive and requires frequent updates to memory. Inference, on the other hand, uses a trained model to make predictions, with fixed weights and lighter compute requirements. The TPU V1 was initially designed for inference, delivering massive speedups over GPUs and CPUs. However, as AI models grew more complex, the need for efficient training hardware became clear, leading to the development of subsequent TPU generations. In 2015, Google deployed the first-generation TPU in its data centers. The results were staggering. TPU V1 delivered 92 TFLOPs using int8, making it 70 times more efficient than comparable GPUs and 200 times more efficient than CPUs for inference tasks. This leap was achieved by focusing on compute intensity, maximizing the percentage of cycles spent on actual computation rather than memory or control overhead. The TPU v1's architecture was a game changer, but it was just the beginning. The TPU family evolved rapidly. TPU v2, launched in 2017, added support for training and introduced BF16 floating-point operations. TPU v3 improved further, delivering 123 TFLOPs and supporting both training and inference. Each generation brought architectural enhancements, high bandwidth memory, faster interconnects, and improved cooling. By 2025, TPU v7 achieved a peak of 9,228 TFLOPs, using INT8, a 100x increase over v1. These advances were driven by a relentless focus on performance per watt and compute efficiency. The TPU success is rooted in 5 core design principles: rapid iteration, domain specificity, streamlined memory, and I divided by O quantization, and a focus on one problem at a time. By iterating every 2 years, the team could quickly deploy improvements. Focusing on matrix multiplication and addition allowed for extreme optimization. Streamlining memory access reduced energy consumption, while quantization using 8-bit integers and later BF16 balanced speed and accuracy. Tackling inference first, then training, ensured early wins and continuous progress. Matrix multiplication is at the heart of neural network computation, but it's a computationally expensive operation. The time complexity grows cubically with matrix size, making large-scale AI models extremely demanding. To address this, the TPU leverages both algorithmic improvements and hardware parallelism. By running multiplications in parallel and reusing intermediate results, the TPU dramatically reduces computation time and energy consumption, making large-scale AI practical. The breakthrough enabling the TPU's efficiency is the systolic array. Imagine a grid of processing elements, each passing data to its neighbors in a rhythmic, coordinated fashion, much like a heartbeat. This design allows each data element to be read once, used multiple times, and written only when the final result is ready. By minimizing memory I divided by O and maximizing data reuse, systolic arrays achieve high compute intensity and low latency, making them ideal for deep learning workloads. At the core of the systolic array are the processing elements, PEs. Each PE receives values from its neighbors, multiplies and accumulates results, and passes data along the array. This interlocking design allows for massive parallelism and efficient computation. By carefully orchestrating the flow of data, the TPU can perform thousands of multiplications and additions in just a few clock cycles, unlocking unprecedented performance for AI workloads. The power of systolic arrays becomes even more apparent as we scale up. For example, a 4x4 systolic array can multiply 2 4x4 matrices in just 10 clock cycles, compared to over 100 cycles with traditional architectures. Each row from matrix A and each column from matrix B flow through the array, intersecting at processing elements that compute partial results. This scalable design is what enables the TPU to handle the massive workloads required by modern AI models. Behind the TPU's success is a world-class team of engineers and researchers, led by visionaries like Jeff Dean, Cliff Young, Norman Juppy, David Patterson, and Nishant Patil. The team combined expertise in computer architecture, application-specific design, and high-performance systems. Their collaborative spirit and relentless focus on efficiency transformed the TPU from a concept into a cornerstone of modern AI infrastructure. The TPU's legacy is not just in its hardware, but in the way it redefined what's possible in computing.